introduction to path analysis. So we're going to learn some basic stuff, the terminology, the concepts, and in what kind of typical research scenarios we're going to use path analysis, and what kind of research questions we are going to construct. If you are thinking of, you probably can use a path analysis. So we're going to cover 3 aspects in today's presentation. First, we're going to describe what is path analysis, and I'm going to introduce some key terms, terminologies, and also we'll try to conceptualize the path model and path analysis. And then secondly, we're going to identify research questions or hypotheses that can be answered by path analysis. And thirdly, that is the most important part today, we're going to describe how to conduct a path analysis in Mplus with an empirical example. So we're using real data, and we're trying to see how we can perform that step by step in Mplus. One thing to add is we can perform path analysis in many other software programs, in Stata or R, SAS, and many others. So if you are interested, we have the supplements materials for the syntax in Stata or in R. If you're interested, you can contact me later after the talk. So what we will learn today, we start from describe path analysis. What is path analysis? It is developed by a guy named Sewell Wright, a geneticist in 1918. It was way back in time. And it is a modeling method used to determine if hypothesized paths occur as expected among a set of observed variables. I would like to give you a small analogy to help you understand why it is important to think about paths and observed variables when you do path analysis. Like, pretend you are an architect and you have a blueprint. You want to build something, and then you start from setting up the framework, which are your paths. So they're like beams and pillars of that building, and then you're gonna have your building blocks. You have your bricks. So you put them together, and you already have that blueprint in your mind, whether you want to build a simple cabin, a simple house, or a more complex mansion. So you can do that with your past and observed variables. We can start, if that's too much for you to take in, if this is the first time you ever heard of path analysis, we can start from regression, which you already know. Okay, we start from the simple linear regression, and that can be represented in a way as a path model. So say you have this outcome variable of your primary interest, which is college GPA. And you have observed sometimes the high school GPA help to predict that person's future college GPA. So that's a simple linear regression. And then we have our famous regression formula. You got your college GPA and intercept plus slope times high school GPA plus random error, and that's your regression formula. This, in a way, is a path model, because you see there's a link, unidirectional, from high school GPA predicting college GPA. Now, if we want to push it one step further, we think about multiple linear regression. It can also be represented as a path model. So instead of a one IV, which is high school GPA, you have another IV, ACT score. You have observed not only high school GPA, but also a student's ACT score helps to predict the final future GPA. So we have this multiple regression. You have an extended regression formula. Let's think about simple mediation model. This is one step further from the multiple regression, because your IVs do not simultaneously predicting your outcome. There are some other stuff going on among those IVs. So the relationship does not only happen between your IV and DV, but among those IVs. So give you a simple mediation diagram. If you see the top one, this is simple linear regression, right? You have your one IV, one DV, and that IV directly predicting that DV. This one without mediator. one is a simple mediation model. You have not only IV and your DV, you have a mediator. So we're saying that your IV probably have some kind of influence on DV, but not only directly, but also indirectly through the mediation of this variable. Therefore, you have how many paths? 1, 2, 3, A, B, C, right? 3 paths. So now you have noticed that I put error terms on DV and MV. I'm going to explain when we talk about the variables in the path model why we should do that. So direct effect is the C path. Indirect effect from IV through mediation to DV is A times B. So it's product of the indirect effects along that path. So if there are other paths and it's indirect, you also multiply all those indirect effects. And then we talk about the variables, the building block. Again, using this diagram. So there are basically two types of variables in path model, exogenous and endogenous. So exogenous, one way to identify that is, yes, it's one of the IV, your IV, and you only see the arrows coming out of it. So exogenous, you only have arrows coming out of it. What does that mean? That means no other variables in your path model cause your exogenous variable. So that's exogenous variable. Endogenous variables can have arrows going in or going out, coming in or go out. That shows you your DV, of course, is an endogenous variable because you have arrows coming in, right? But your MV is also an endogenous variable because even though it has an arrow going out, it also has an arrow going in. So it is caused by some other variables in your path model. Okay. Oh, then we can talk about the error terms. In your path model, we should add the random error terms to all your endogenous variables, but not your exogenous variables. Okay, now back to this diagram. We still got the direct effect. We got indirect effect, product of the indirect effects, and we got total effect, that is the direct effects plus the indirect effects. Okay, so that concludes our description of a path analysis. Very simple. I hope that it helps you have a clearer understanding of that. If you have any questions, you can ask me after the talk. And then we talk about, we can identify some research questions or hypotheses that can be answered by path analysis. Now, what constitutes a typical path analysis RQI or hypothesis? It all starts with your DV. You have seen a variable of your primary interest. You see that, you want to know what caused that, what affects that, what influences that. It all starts from your DV. It can be DVs, multiple dependent variable, and you have a set of independent variables. So you notice not only one relationship or one link, but multiple links, which involves multiple factors. Now, you want to know, first of all, the causal links between the IVs and your DV. I put causal in the parentheses because in the path model, the links may not always be causal. So I put that in. But most of the time is because you see the direction are unidirectional, so one, at least in time, happens first, and then you get the other one. So between the IVs and DVs. But that's the first step. Second step, you want to know the causal links among your IVs. like what I said in the multiple regression, you do not expect them, all your IVs, to have certain effects on your DV simultaneously. There must be something else going on among them. So you want to know the interactions or relationships among the IVs. And then, most of all, you want to know which links. Now you have a lot of links, right? So which links have more impact on your DV than others, okay? So those are very typical path analysis hypothesis. Now I'll give you a hypothetical research scenario. Let's say I am interested in obesity. That's my DV, okay? And the obesity is quantified in our case using BMI, okay? So that's obesity. And then I have observed that many other factors probably attributing to a person's situation and with, involving obesity. For example, a lot of screen time, loss of focus, irregular eating habits, not enough sleep, eating a lot of junk food, no exercise or very little exercise. So I have a lot. I have 1, 2, 3, 4, 5, 6. I have 6 of them. So all those are my set of IVs. Now, can I enter all the IVs into in a multiple regression model and to see combined all of them or alone how they affect my DV? Yes, you can. Sure, you can. But at a closer look, I see there might be something else happening among them. For example, sleep deprivation. Could that be caused by I spend too much time watching TV or using my computer? And I see irregular eating. Well, is it because I eat a lot of junk food and then I'm constantly full so I don't want to eat? Or is it because the habit of eating a lot of junk food, is it because I spend a lot of time watching TV so I'm more exposed to junk food ads, advertisements, so I eat a lot of junk food? And maybe because I eat a lot and watch TV, sitting on the couch a lot, so I have little to none exercise. So there might be something happening there. And therefore, we're going to ask, does screen time affect BMI directly? Or does it affect something else first? For example, exercise, which in turn affects BMI. My second question could be, does screen time affect not only one IV, exercise, but several other IVs together, and then which in turn affect BMI? So probably screen time affects exercise and junk food, and then which in turn affect BMI. And the third question, if several other factors, like in our case, are involved, which of them have more impact than others? And therefore, you could end up with this. So you got your path model. This is a hypothetical. It's not theory-based. So we're saying, for example, screen time causes sleep deprivation, and that in turn causes loss of focus, and then that causes the sleep deprivation causes obesity, and so forth. We have some published examples of path analysis. There are a lot. If you go into the literature review, you can easily come up with a lot of path analysis research studies. One of these I'm going to show you is way back 1980s, but I think it's kind of interesting because they want to know the role of mathematics self-efficacy in the choice of college men and women's math-related major choice of math-related majors. So the purpose of their study, they want to know the causal model between the math-related major choice, which is their DV, utilizing math self-efficacy, that's efficacy, as a major mediating variable. Why major? Because if you see this model, there are a lot of mediators in here, right? Like math anxiety, math ACT scores, and and years of high school math, actually the only exogenous variable is gender, right? All the others in the middle could be viewed as mediators. But they are interested in this major one, so math self-efficacy. So their major hypothesis is math self-efficacy, if influenced by gender, socialization. Socialization is a kind of a scale measured by the masculine score, MSRI, and math level and math background is more strongly predictive of the math major choice than any of these mediators alone or combined. So it has to go through the mediation of math self-efficacy, then you can see a stronger predictive path. So another published example of path analysis. This is interesting. It is a path analysis of a biobehavior under conditions of crowding. So you can see they have multiple DVs, dependent variables, but they can be viewed as a same category. We can say that psychological, the yellow one, are psychological evaluation of shoppers' shopping behavior. Now, PC, as you can see, the green one, the red one and the blue one, they are the crowdedness. The blue, physical density, is kind of an objective reflection of the crowdedness. The red type, the confined feeling and restricted movement, are PC, their perceived crowdedness. So they constitute the environment that the shoppers are exposed to. So that in turn will have certain effects on shoppers' changes in their shopping behavior, like the manifested in the green variables. And that will predict the psychological evaluation of the shopping trip. So now let's switch gear and talk about the path model, how we estimate it, how we identify that, how we specify that. When we specify a path model, you need to keep in mind the differences between just identified and over-identified, which will be useful in the later stages when you estimate your model. So this is a simple diagram. We have 3 variables, 1, 2, 3. And the variable 1, by our definition a few slides previously, it is exogenous variable because it only has arrows going out, right? 2 and 3 are endogenous variables. Now we can see all of them, all 3 variables are connected to each other with a direct link. Do you see any missing link? No, this model has all the links. They're directly linked to each other. So we call that a just identified path analysis model or a saturated model. Now, if we take away a direct link, we will have an over-identified model. I just give 2 possible scenarios. In this scenario, again, we have 1, 2, 3. Again, we have 1 as exogenous variable. We have that predicting 2, and through 2, mediation 2 predicting 3. However, we see a missing link between 1 and 3. Now, in the second model, a slight change. Here, 2 become the exogenous variable. 1 and 3, 2 directly predicting 1 and 3. But again, we see there's zero relationship between 1 and 3, which is ridiculous in practice. How can you be sure these 2 variables completely have no covariance at all, and no correlation, zero correlation. That's ridiculous. So this is over-identified path model. So both models are, because they attempt to explain the correlation between 1 and 3 in the absence of any direct effects. So we're done with the questions, research questions, and hypothesis. Now we're going to describe how to conduct a path analysis in Mplus. So what are the general steps? Before we go into the steps, you need to start with data preparation, right? So we need to understand our data. Probably you're gonna request sample stats when you run it in Mplus to see the distribution, frequencies, the kurtosis, normality, missing data. So all that stuff, you need to make sure you understand your data set. And then you can start perform the path analysis, which I have listed 6 steps here. So you start with specifying your model. Basically, you want to draw out, right? You want to see what are the exact links between these all different variables. Secondly, you want to enter that into Mplus, specify that you want to estimate. You want to get your estimated model fit indices, and then you want to evaluate the model fit. And then you want to examine your results. If your results tell you something, now step 5 is controversial, but we will talk about later when we get there. So we will see if it is necessary. Probably we will modify the model, and then if you modify the model and re-specify that, you need to go back to step 1 and repeat steps 1 to 4. And then finally, if you think that is okay, then you examine the results and report. Now I have to emphasize that the step 6, examine the results, I said when you think it's okay. It does not mean that you have to keep modifying your model and re-specifying your model until you have a good fit. And then you examine and then you report. That's not so. So if you end up with a bad model, you just report as it is. Now our research scenario is about money. So, major hypothesis is we hypothesize that an individual's financial knowledge and skills will positively impact his or her financial action. By financial action means whether he or she follows through on his own financial goals. And then financial well-being, which in turn will positively affect that person's overall life satisfaction. So you see that I intentionally colored the DV in orange, which will be consistent till the end of the presentation, and the IVs in green. So when you see green, you know that's IV, and the orange is our DV. So data preparation, we need to know our data. It is taken from the data from National Financial Wellbeing Survey conducted by Consumer Financial Protection Bureau. It is publicly available. It was published September 2017. It's a huge data set. It involves 290 variables. We only selected 5 for our demonstration purposes. So these are 5 selected variables. Again, green is IVs and orange is DV, and it's a huge data set. It's 4,980 observations. So, subnode, that's our financial knowledge. It's a single item score reported on 1 to 7, like Likert scale. Financial skills is already reported in the form of RT scores, ranges from 5 to 85. ACT is a single item score on a 1 to 5 Likert scale. FWB is financial well-being. Again, that's reported in the form of RT score, range from 14 to 95. And SWB is life satisfaction, single item score, 1 to 7 Likert scale. So we specify our model. If you recall, these 2 light green ones, we call them exogenous variables because they have arrows out. This one is financial knowledge. This one is financial skills. We hypothesize that they will through the mediation of financial action and financial well-being to have a positive effect on overall life satisfaction. That is our DV. Now, may I ask you to take a closer look at this model and remember what we talked about, what makes a just identified model. Do you see any missing direct links here among our 5 variables? Do you see any? Okay. Hold on to that thought. We'll come to that. Before that, I'm going to talk a little bit about different estimators or estimation methods in Mplus. There are many, but we're going to focus on ML, MLR, and WLSMV. Okay, so just 2 points to emphasize. First of all, if you have continuous data, you don't want to use WLSMV because that's for categorical data or ordinal data. If you do have continuous data, if it's normally distributed, your data is great, then you can use ML. If it is not normally distributed, it violates the assumption of normality, probably then you want to use robust maximum likelihood. When you are doing this, of course, you want to do the preparation of data. You can run a normality test. But since we are using software to run everything, so it's fast. So you can quickly run ML and MLR and then compare the results and to see if there's a drastic difference in terms of SE, standard errors, on their point estimators. If there are certain differences, but that's not drastic, and you'll be able to draw the same conclusions or you get to the same inferences about your research questions, then it is okay to go with ML. That means the violation of normality does not have a huge impact on your conclusion. If then that's a huge difference, and you will be able to draw different conclusions, then you have to go with MLR because your data really cannot be assumed to be normally distributed. Both of them handle missing data, ML and MLR. So if we estimate that in Mplus, this would be a typical syntax. We enter the file, and then I have simplified the data set. So I only have 7 variables in that. So we're going to use 5 of them. Missing data. For the demonstration purposes, I mistakenly, ignorantly deleted all my missing data, which is not advisable because Mplus, ML, and MLR can handle missing data. So the original missing the data says if the respondent fails to respond to a certain item, it will be represented by -1. If the responses are illogical or doesn't make any sense, it will be symbolized as -4. So we will say missing data that. And model, you can take a look here. It's actually 3 sets of regressions, right? So I mean, it doesn't matter in which order you put in these regressions, but I just do it from the beginning of the past model to the later stages towards the DV. So you can ACT regress on knowledge, financial knowledge and skills, financial well-being regress on financial action, another mediator, financial knowledge and financial skills. And then the overall life satisfaction, which is our DV, regressed on all other 4, right, of the variables. So financial well-being, financial action, knowledge, and skills. For the estimator, we used MLR for the demonstration purposes. For the output, we requested sample sets, so you can see your data sets more clearly. And then we requested standardized residual, which will be used for later estimation and evaluation purposes, especially for evaluating and making judgment call about approximate model fit and model modification indices, right? Modification indices. All right, then we examine the model fit. We will start with exact fit. For the exact fit, we go take a look at the chi-square, and we want the chi-square to be insignificant. We want the p-value to be greater than 0.05. That means we have a good fit with our estimated model, and the real data have good fit, exact fit. If that is not tenable, then we go see the approximate model fit values. So we have SRMR, standardized root mean square residual. We want it to be smaller than or equals to 0.08. And we have RMSEA. We want it to be very, very small too, like smaller than 0.06. And then we're TLI and CFI. We want them big, though. We want them to be so big, at least bigger than 0.96. But a word of caution is be mindful when you use these cutoff values, because they're not without controversy, and they're not like strict standards. You have to do this, and then you got the approximate fit, because it varies with your data, with your research questions, with the specific context you are working in. So be very careful of that, about that. If we have insignificant chi-square value, then we can say it is good fit. Regardless, then you don't need to look further. You don't need to look at the approximate model fit things. And then if that is tenable, and if chi-square is significant, but you still have your SRMR smaller or greater than 0.08, and then plus, remember we requested standardized residuals. So we look at the residual correlations. If there is no big correlations, then we can say we have approximate model fit. So then we display and examine our results. This is a typical output in Mplus. First of all, we take a look at chi-square. Oh, you see the degree of freedom? What you got? Got a 0. You have your RMSEA. Remember the cutoff value we say we need to use for reference. This should be smaller than what, 0.08, right? But you got so good. And then you got CFL and TLI. We want it to be greater than 0.96, right? But we got 1. And then the final SRMR, we want it to be smaller than 0.06, right? You got 0. And what happened? So it's my computer program going wrong or anything. But do you remember the original specified model? We had a saturated model, right? All the 5 variables had connected to each other with a direct link. It is a just identified model. That's what you should get. That's a perfect fit, right? If you don't believe me, we can go further and take a look at the standardized residual correlations right there. So this conceptually, we're saying the original correlation matrix minus the estimated model reproduced correlation matrix, and to see if there is any residuals left, right? So theoretically, we want it to be very small. If it is 0, then we say, well, all the covariances between the variables are explained by our model, so it's great, it's perfect fit. If it's very small, then we say it's good, right? So explain a large amount of it. But it's large, then it's bad. But let's see here, you got zeros. So we got perfect model fit. Okay, because as you know, we have a just identified model. Okay, these are local model fit values. These are basically the standardized path coefficients and beta weights. So in the Mplus, if you request standardized, it will give you both unstandardized and standardized path coefficients, which you can compare to each other and take a look. And these are your p-values, and it suggests that all our path coefficients are significant, right? They're all significant. Although you can see some of them, like this one, subject knowledge, which is financial knowledge predicting overall life satisfaction, is quite small, right? It's 0.05. Think of it as like regression, standardized regression beta value. And the financial skills predicting overall life satisfaction is also quite small, about 0.06.
So here you can see the diagram, the specified model with our standardized and unstandardized estimates of the path coefficients plug in. And in the parentheses, that's unstandardized estimates. All coefficients are significant, but you can see clearly there are some very strong paths. For example, the strongest one is financial actions predicted by financial skills, which the standardized coefficients is 0.625. And the second strongest one is overall life satisfaction predicted by the financial well-being. And the standardized estimates is 0.401. If you look at the values within the parentheses, we can also identify some of the weakest ones. We can see the weakest ones is overall life satisfaction predicted by financial skills. Then the coefficient, the unstandardized estimates is only 0.007. And also, the overall life satisfaction predicted by the subject knowledge of finance is also very weak. The unstandardized estimates is only 0.063.
Okay, now we talk about modify and respecify the model. As I said, path models or any other model, CFA, SEM, should be theory-based. You should start from a theory. The theory tells you certain links are possible, certain links should be present, other links should not be present. Then that's the foundation of your building your model. However, if you start from theory-informed hypothesis, you want to see if that works, then you might have some feedback after you run this model to tell you how to respecify and modify your model. But again, everything starts from theory and ends with the theory. We want to check if we see the model fit indices and there's something that does not make sense. Probably you can think about, what if I remove that link and what happened to that? Remember, pay attention here, I said trimming. Trimming because we want to drop, right? I did not say add, because we start from a justified model, so anything we should do is to drop, to trim the model. So this criteria, so-called criteria, not real criteria. A lot of researchers do not agree on that, so they are controversial. When you trim your model, you need to be careful that you want to delete one predictor or one path one at a time. Because you remove one path, they may change the beta weights or path coefficients of the remaining path or predictors. Some may not change. I'll show you, okay? So if you delete one variable at a time, you remember when we talk about steps, you go back to step 1 and repeat steps 1 to 4 again. If you really want to delete 2 or more predictors or paths at one time, simultaneously, you probably want to conduct a chi-square difference test to see if that model, trimmed model, significantly differed from the original model. If it does, you cannot do that, right? You go back and delete one at a time. So let's do this. There we go. So you remember that the path was, and it's no longer there. We deleted it. Okay. So we compare our two models. On the left side is our saturated model to begin with, and on the right side is our trimmed model. And what we're looking for, you can compare them to see mostly the syntax is exactly the same. The only difference is here, right? We regress life satisfaction on all our IVs. Here we delete financial knowledge. That's the only difference. And then we display the results and compare them. So we start from chi-square, right? From the exact fit values. Here, because we have saturated model, so we have degree of freedom of 0. Here we have df of 1. Why? Because we delete that path, right? Before we have the p-value of 0.00000, and now we have a p-value of 0.0061, not much, but you know, it's there. And then we compare the RMSEA. We have perfection here, okay? Now here we have 0.036. Remember the cutoff value, it should be 0.08, right? So we say, well, it is below the recommended or reference cutoff value of 0.08. And then we take a look at CFI and TLI. That one is 1, this one is 0.999 and 987, above the reference cutoff value of 9.96. Here, this one we got 0.08, so not too bad. These are approximate fit. Why do we do that? Because even though we delete that, we still got a significant chi-square value, right? So we do not have an exact fit. So we go and take a look at this to see the approximate model fit. And then we want to take the final look at the standardized residual correlations. Before we have all 0 residual correlations. Right now, we have mostly 0, but with one little exception here, between overall life satisfaction and financial knowledge of 0.031. This is their covariance. Remember, we removed this path, right? We removed this path between this, and now they have unexplained residual covariance. But that not too much, right? It's not above 0.1. It's 0.031. So these are local fit coefficients. These are path coefficient. Oh, I'm sorry. Path coefficients. I want you to look at the purple, the pink squares, boxes. You see, they remained unchanged, right? Remember I said delete one path or predictor at a time, because if you do so, it may change the remaining predictors and paths. So here, it happens earlier in the path model, right? So they remain unchanged. However, the different color contrast boxes, you do see some change. So here you have this, and here you have this. They changed. So that happens because you delete a path. Now, after you do this, let's pretend we have already done with risk specification, we examine everything, then we want to report our results. Before that, you need to write up a data analysis plan. It will more or less look like this. You explain all your DVs and IVs and the procedures you're going to do, what reference values you're gonna look at, and to justify your conclusion. And this will be a write-up. You explain the model fits, whether you have achieved an exact model fit or approximate model fit. And then you're going to talk about your path, if they're significant in your model. and you want to explain, interpret the path. Okay? You want to cite this presentation. These are the citations. And the end. Thank you.